is this like a video that you're going to repost later?
This is a live stream.
Oh.
No, thank you.
Yeah, no, I know how to make my videos better. I just choose not to.
That's
So.
understandable.
Okay. Welcome back. We have been covering a lot of very fun concepts in this course. It is a very high level class. So if you're feeling lost, this is a good time to bring stuff up. Also because your homework assignment was a little brutal, and next week's homework assignment, which I am still working on, which will be due Sunday night, which I was hoping to get out before the weekend, but things happen. It's going to be very similar, except now instead of with electric systems, you're dealing with linear translation systems. That is the appropriate response. So last week we covered linear translation systems. Okay, and in covering linear translation systems, I can almost read that. Nice, I'm gonna say that's good enough. In covering linear translation systems, the really important piece that we discussed were that the system setup is very similar to what we dealt with electric systems. Okay? You have the inertial component, which is the mass. You have the dissipative component. I think that's what I called it. And that is the damper. And you have the potential energy component.
Correct.
Nice. Different. And that is a spring. Different people refer to these as different terminologies. I'm at least trying to stay consistent within this one class. This class does not need that level of confusion. Okay? Well, the important thing was we could take a system like this and given a model, you could at least be able to say, here's the math that we use. We talked about the constitutive equations, but we also talked about the different system equations that were involved in this. Anybody remember the different system equations we have? Component equations are different than system equations.
The sum of forces.
You have sum of the forces is equal to 0. That's one of them. That also includes D'Alembert's force. But then we also had conservation of mass and conservation of energy. Okay. So using any of those three equations, we can come up with some kind of equation dictating how the system behaves. What we're going to start focusing on, starting this week, starting on Thursday, is we're going to be talking about why do you need to know all of this math? Why is this all important? What are we really getting at here? But before that, we're going to have one more type of system that we're going to be discussing. Okay? This one type of system is a rotational system. Usually rotation, circular motion is people's least favorite topic when it comes to Physics 1. I was in that boat. I hated that. But we have to talk about it anyways because it is a very important component. All right. When it comes to a rotation system, we're no longer dealing with a force displacement style linear translation system, okay? We're now dealing with different variables. Instead of displacement, what does rotation system use? Angular displacement. Which is just the word displacement with angular in front of it. Instead of force, what does a rotation system use? I was half expecting you to say angular force. It uses torque. Okay, so here you have angular displacement and torque. Angular displacement, the derivative of that becomes angular velocity. The derivative of that becomes angular acceleration. Okay, you'll notice that the analogy between a rotation system and a translation system is very similar. Here, displacement in a linear translation system differentiates to velocity, which differentiates to acceleration. If I just throw angular in front of each of these, it's the same principle, okay? All right, so units for angular displacement is going to be radians. Okay. Yes, you can work in revolutions. Yes, you can work in degrees. However, the conversions start becoming really kind of gross. Working in radians gives you the nice units. I would always encourage you, anytime you're working in a rotation system, convert to radians. Radians make less sense because it's hard to picture a radian, but mathematically it just makes everything easier. Okay, which also means that the other one is a pound-inch.
Why do they switch them?
Huh?
Why do you switch
I actually don't know. I think you could actually call this a pound-foot, too. I don't know. This one, though, I've heard it said both ways. I don't know why this one is always pound-inch, and this one could be a foot-pound or a pound-foot. I don't know. It's a great question. There are other units that can be used. However, they're very uncommon because you have the kip foot. You have kip inches. Kip inch is a really crazy unit, but I have seen it used in a professional setting. I have seen it. It's actually not that uncommon. But these two tend to be the most common. In the metric system, the units typically tend to be the Newton meter or the Newton millimeter. I've never seen a Newton centimeter used realistically. It's a Newton kilometer. That is ridiculous. Instead of doing a Newton kilometer, they tend to go with a kilonewton meter, which is the same thing, just written slightly different. Okay. All right, any questions on units? This is all baby stuff. This is stuff you should have known when you were 2. And your word of today is Newton millimeter. Huh? I had a really great daycare. They were sitting here like, this is a force balance. You need to make sure it sums to 0. Very good. Do you need to use the potty? No, I already did. Okay. All right. By the way, all of this is on the live stream, so you can watch the first 10 minutes, catch up. So as we talk about rotation systems, the thing that we did when we introduced linear translation systems was we talked about the three components. Okay? Once again, we're going to have three components to a rotation system. We have the inertial component. Does anybody know what that is for a rotation system?
Talking about what element?
Yeah. So for a linear translation system, it was mass.
Oh, it's still mass.
It's not mass.
Rotational mass.
It is rotational mass. That has a very specific term. Remember, we throw the word angular in front of everything. Angular mass. This is called the moment of inertia, which you've all had some experience with.
That's less cool than angular mass.
Actually, I have heard it called angular mass before. I've never heard it called that very often, but I have heard it called. Some brilliant minds, they just get to make up their own terms. Whatever. Okay, so moment of inertia. What is the moment of inertia?
The point at which the forces are revolving.
It's not quite.
This is the moment at which you put like something into motion. Like the amount of force needed.
Kind of. The way that I like to explain moment of inertia is like this. Zach, get up here.
Scared. Backwards.
Okay, hold this. Just hold it like that.
One hand?
Yes. Now, rotate it up and down a little bit. Is it pretty hard, pretty easy? Okay, now let's make it a little harder. Tell me, Jack Sparrow, do you fear death? Okay, put it straight out. I'm now going to add, 500 grams to it. How hard is that?
Not very hard, but a little bit harder.
Should be a little harder.
So, like the meter stick is gonna snap.
It might actually. So why is that so much harder?
Because that has more torque.
It is more torque.
Farther from the moment of inertia.
The moment of inertia is a measurement of the mass at a distance from the rotation point. Thank you. Okay, and if all of you want to prove to yourself that that works, this is a great example. Because this is manageable. This is Zach is doing his workout beef. This is how he gets pumped up for a game.
Meter stick lifts.
Meter stick lifts. Yes. So I'm trying to find the exact formula so I don't write it down wrong.
Just outside of the frame of the rotation, so you use the meter stick.
Nice. Okay. I was wrong, so I'm glad I looked that up. Your moment of inertia is given by I. The definition of moment of inertia is I is equal to the integral well, that's not right. Nope, trying something else. I don't like that formula. Come on, Wikipedia, give me answers. Shh. I trust Wikipedia more than I trust any of you. Oh, dang. I'm trying to figure out what the integral is. It's just, okay, interesting. So, the way that it's presented is the moment of inertia is the integral of the distance squared multiplied by the integral of the mass. So basically it's how does the mass distribute across a distance? And as the mass changes, what radius is it at? Now I will say the whole reason I don't have this one memorized is because no one uses this, realistically. It ends up being a planar situation because it doesn't matter what the position is along the axis, it only matters how far away it is. So here, if Zach had, instead of a meter stick, had a stick that was this wide but weighed the same, you'd have the same interaction both ways. Okay. So, what we have out of this is that the distance to each mass is proportional to the square, or no, the moment of inertia for each particle of mass is proportional to the square of the distance to its rotating center. Okay, so here when we're talking about moment of inertia, if you have a wheel, I don't know if I have a nice, good, thick wheel in here. Let's see if I do. This will be good enough. Where is the center of mass on this triangular chunk of metal? It's right in the hole, okay? So if I rotate it about that center, does this have no moment of inertia?
No, incorrect. It does.
It does have moment of inertia, or it does not?
It's proportional, so I mean, it could be 0, but the proportion could be.
Zach, get over here. Here's your stick. Stand in the frame so people can see you this time. Hey, you can't deprive Duncan. All right, so now I have two 500-gram masses. I want you to grab that at the center of the stick. Okay, now tilt it up so I can hang these from it. Like that.
Got it.
All right, so you're holding, well, 50 is the center.
Yeah, it's 50.
So yep, grab onto the 50. So what I will do is I'm going to put one at the 40, and I'm going to put one at the 60. Okay? So the center is still right where your hand is, right?
Yeah.
Okay, so now do this. Is there any difficulty to rotating it?
I would say no.
Not terrible. All right. So let's play with this again. Now I'm going to put this at 10 and 90. So once again, the center is right where your hand is. Now rotate it. Is it harder?
No.
Yeah, I think
I mean, it's a little more off balance, I feel like, but it feels like it takes the same amount of power.
it needs heavier weights.
Yeah, well, there's two moments that are acting in opposite directions. So
They are acting in opposite directions.
there's 0 net moment.
Yeah, created by both because he's holding it right at the center.
And so when you rotate it, it's the same moment acting in each direction.
All right. So,
So what's the correct answer?
well, let's try this again.
It's just too small.
Let's just verify.
Give them the right answers.
I'm not giving you the right answers yet. Try it again. Is it harder or easier? You're going a lot faster.
Okay, so we're going slower.
Yeah.
Okay, put it back. I feel like you might have picked a bad version for this.
Huh? Because you're so jacked? Bro, lift the steroids.
Oh, Maddie. Go really fast.
Yeah, you're going really, really slow now. Now you're going faster. Harder or easier?
Once you hit the edge, it's a lot harder to go back.
Thank you. All right, somebody else want to try this? Is it the same? Skylar, get over here. I trust Zach too.
Zach's judgment.
Okay, grab it at the 50.
I told Dylan to get out of here. Now he's not going to be able to see me.
Okay, first of all, start rotating it. Okay, then we have a good feel for it. I'm gonna put this at 60, put this at 40. This should be a lot, well, no, because this is at the center, you do have more mass to rotate, but harder or easier? Harder, easier, or the same?
I feel like it's the same.
Roughly the same? Okay, now we'll try it at 90 and 10.
Definitely a little harder.
He says it's harder.
Yeah.
You gotta spin it as fast as you were spinning it before. That works too.
Too fast.
Too much beef. Okay, can you say that you feel like it's a little harder, a lot harder,
Just a little.
just a little harder?
Yeah.
It is nice though because you have the balancing masses.
Yeah, I wouldn't, I mean,
Okay, let's try it back at 10 again, 10 and 40. 10, well, 60 and 40.
This is like nothing.
It is like nothing.
yeah.
Do a Darth Maul spin.
Please, please. I'm standing over here. Okay, so now we have one person who says it's like nothing because apparently he's made entirely out of 100% beef. Like, don't get into a fist fight with Zach. It's a good bit of self-promotion here. It's like nothing. I didn't even know it was there. In reality, it actually is harder. It's about 3 times harder to rotate it when the masses are at 90 and 10 versus when it's at 60 and 40. Okay? About 3 times harder. As much as we trust Zach, Zach let us down with his absolute, just massive muscles. Monster. It's the inner wolf. So that brings about a problem. Because we know in both of those situations, the center of mass was located right at that pivot point. But it is harder to rotate it when it's farther away. Why?
Needs more torque.
It does require more torque. Why? It does, each one of them has a higher moment, yes, but those moments counterbalance. Comes back to our first example, okay? When I do this, and I rotate this up and down, okay, I'm going to try to do this at a relatively constant speed. If I move it up and down like this, if I move it out here, like this, how much faster is it moving? So here, case 1, I put it right next to my hand, and I move it up and down at this speed. Case 2, I put it here, and I move it up and down at the same speed. How much faster is it moving in case 2 versus case 1?
No, it's the same speed.
It's traveling at the same speed. Now when I rotate it, try to keep it at a constant angular rotation, here, it's traveling at a specific angular speed. I keep the angular speed constant, and I move it like this. How much faster is it traveling now? It's significantly faster.
Bigger radius.
The farther away, yes, the farther away you are from your center of rotation, the faster that mass moves. Okay?
That's why it's harder.
That's why it is harder for most people who aren't Zach. You never know what you're going to get when you have a student do a demonstration for you. This is one of those like, yeah, you just kind of have to own that that happened, and okay, thank you.
I ended up saying it was heavier.
I know, but you were hesitant. So I need, yeah, just too much. Bring your Super Scion to class. Okay, so the farther away you are from the rotation point, the faster you travel per the same angular velocity. Which is your radius, as Zane pointed out. Okay, so for the same angular velocity, you travel at a faster speed when you're at a higher radius. And the whole reason for that is because we have the relationship V is equal to R times omega. All right? Now, if we were to integrate this, what you get is roughly that your acceleration is equal to R times alpha. That acceleration is centripetal acceleration. It doesn't account for tangential acceleration, which I think you guys talked about a little bit in dynamics class. At least you should have. So what this means is, when we talk about F equals ma, if we were to replace this A with the expression R alpha, here's what we get. The force required to lift that object, or force applied to that object, is equal to m times r times alpha. Now if we look at it as a torque, torque is equal to m times alpha times a certain radius. It's a force times a radius. If we plug in this value for A, what we get is mr squared alpha. Mr squared here is our moment of inertia. It represents a point mass. Okay? So this is why it does not matter if the center of mass is at a certain point. All that it matters at is how far each individual mass is away from the center of rotation. If you have a wheel, the center of mass for that wheel is always going to be right in the center. Otherwise, it's an unbalanced wheel. When you spin that wheel does have some rotational inertia to it, which is why you can't just apply a little bit of torque and it spins at an infinite speed. If it had no rotational inertia, that would happen. So when it comes to rotation systems, we have to keep in mind the inertia is not, it does not behave like mass, because it is a mass at a distance. and it is all masses at a distance. Okay, we're going to get into a little bit more of that when we talk system equations. Well, now we have the dissipative component. Dissipative. What was the dissipative component for a linear translation system?
The damn.
It was the damper. Okay? What did the damper do? Oh, that's wrong. It took energy that was in the system and it released it in the form of heat through friction. Okay? What a rotational damper does is it does the same thing. It takes energy in the system, it converts it into heat, it releases it out of the system. Okay, so this is almost exactly identical to what we understand about the translational bearing. There is an added component to this though. Pretty much every single rotation system has to have some kind of bearing that it rotates about. It has to have a point where it rotates. Most systems have some kind of a bearing or constraint at that location that it rotates about. Okay? So usually your rotational damper is just the friction inside of the bearing. We're going to assume that this is viscous friction again. That's an assumption we made in the last one, which allows us to put together our formulas. Here, the formula for the relationship between, well, I guess we'll get there. We'll get to component equations. But we're going to assume it's viscous friction. Last component here is the potential energy component. What was the potential energy component for a linear translation system? And so now we're going to throw the word rotation on it. And this is going to be a rotational spring, also known as a torsion spring. Check and make sure my audio is still working. Audio is still working. Okay. Thank you for pointing that out. All right, so potential energy, this converts angular displacement into torque. You rotate one end of the spring relative to the other end of the spring, it creates a torque in the spring. Now, there's one reason why this is very important. I've told you before, if I push on this table, it compresses the table. This table acts as a spring. Okay? What that means is a certain amount of load on this table will cause a certain amount of displacement, which is how a spring works. There's actually a spring constant associated with this table. There's a spring constant associated with your skin. There's a spring constant associated with everything. Because in the presence of any load, every material is going to displace. Now, some of those have a more viscoelastic behavior, but that's way beyond this class. It's something you usually learn in grad school. But the important part about that is that means if you have something hit something else, like a football helmet, your football helmet itself doesn't have any springs in it. But it does store that energy. If you push down on that helmet, there's going to be a displacement of that helmet relative to your head. That's the spring constant of your helmet. And that's true. It's actually a different spring constant depending on which angle the impact is coming from. That's true for everything. Every time you hit a golf ball with a golf club, there's a certain amount of force being transmitted from the ball into the club. The ball itself displaces because it has a spring constant. The club also displaces because it also has a spring constant. That is true for rotation systems. If I take this stick, I grab onto the two ends, and I apply a small amount of torque, the two ends will displace relative to each other. Now, I'm not going to do it too much because I would just shatter the stick. That's not something you want to do on a live stream. But this is true for shafts. Every time you have any amount of torque being carried by a shaft, there is a small angular displacement between the two ends of the shaft. Okay? It has a relationship between torque and angular displacement. Nope, that's not it. Okay. Now let's go on and discuss component equations. Well, no, we'll start with system equations. As we summarized in this start of this class, there are three system equations that we have when it comes to linear translation systems. There are three system equations that we have when it comes to rotation systems. One of them is the sum of all torques about your axis is equal to 0. We'll just replace F with a T. And then we also have the conservation of energy and the conservation of mass. I feel like we've seen this before. Wow. We also have component equations. What are component equations? Right, it's the relationship between variables for a component. Okay, physically measured, physically calculable. So here we have three different kinds of components. We're going to have three different kinds of component equations. That kind of goes to say for itself. For the inertial component, we have torque is equal to I times alpha. What is alpha? It's the angular acceleration, okay? Which means this is equal to I times theta with 2 dots over the top of it. Again, component equations link your 2 variables together inside of a component. Anytime you have a mass that is spinning, this equation is true. You'll have to find out what the I value is based on where that rotation point is. This is always going to be true for every rotating system that has any amount of mass. We have the dissipative equation here. Torque is going to be equal to B times omega, where B is going to be equal to your rotational damper constant. It's the viscous friction constant. Omega, whoa, that's not right. Well, let's just write anything. Nice. Omega is equal to theta dot. Again, correlation between your 2 variables, your force variable and your displacement variable. Lastly, you have your spring equation. That one's pretty easy. What you will notice is that for these 3 equations, they're almost identical to the linear translation system. F equals ma. F equals your, I think I called it D. D times V. F equals kx. They're the same things.
Can we just replace the equation that we found last time with the variable for...
Yeah. Yeah. Yes, you're going to need to know that for your homework for next week. You're going to save yourself a lot of time. Give yourself a good chef's kiss. Juicy. Dang it. I need to stop live streaming. This is why I hate live streaming.
Maybe an Italian on now.
Yeah. I'll take it. I actually knew a guy from Italy. He was awesome. He also told me never to go to Italy because it's a giant tourist trap.
Are they the ones that started charging for tourists there? There's a country that started charging entry fees.
Really?
Yeah.
I don't know. It might have been them. I don't know. All right. Now we're not. Once again, I'm not expecting you to solve these problems yet. I am expecting you to understand one critical piece that you're going to need to know in order to do your homework for next week that I didn't really explain in class, but I'm going to kind of cover it here in this class. So I'm going to give you a very, very simple model. Okay? What we have here is we have a circular shaft. The circular shaft is a certain length. It then goes to a wheel that has some thickness. Only one C in that thickness. Okay? Now, this shaft is constrained by a bearing. This bearing sits around the shaft. It's like a circle. It just goes all the way around it. And it is lubricated with some kind of grease. On this end, you have a torsion that's being applied to it, more than likely by a gear or by, perhaps it's directly connected to a motor. But there is a function of torque that is coming in. All right? Bless you. So if we have a distance here, we have a bearing here, we have a mass here, what we have is we have all three components. First of all, this shaft is going to twist when any amount of torque is applied to it. I didn't even have to draw a spring. It's going to twist. Now that twist isn't going to be very much, and if it's a well-designed shaft, it's actually going to be very small. It has a good angular stiffness. Okay? But it still has some stiffness value K that is dependent on the length of the shaft and the material properties of that shaft. Now this isn't mechanics and materials, this isn't machine design, so we're not going to go into exactly how to calculate that K value. I'm just going to tell you it's K. Okay? Okay. Okay? Okay. Okay. Now, we have a bearing. Anytime you have a bearing, there's going to be a small amount of frictional losses. That's something you can't help. The frictional losses are associated with the speed of the shaft. What does that mean? It means if the shaft is not moving, you have no frictional losses. You're not losing energy. Only when the shaft starts to move do you have frictional losses. The faster your shaft moves, the more frictional losses you have. This has a coefficient B. We also have a wheel here. This wheel has a finite amount of mass. That mass is distributed across the wheel at some value. So we'll go ahead and say it's a uniform cylinder. But this wheel has moment of inertia I. So when we spin this wheel, the mass of this wheel is going to resist the movement. It's what you're going to be speeding up. Does the shaft have a moment of inertia? Why?
Because it's a displaced mass.
Because there is a mass associated with it. So I'm going to go ahead and change this to IS and I wheel. There is an associated inertia with making the shaft rotate. So what we're going to do here is we're going to go ahead and write the system equation for this. Okay? Now, usually when it comes to system equations for this class, we pretty much just use the F equals ma and the sum of the torques equals to 0. So I'm just going to write that one out. You can use the other two equations, it's just we don't do them in this class. What are all of the torques acting on this shaft? Here, we have the torque as a function of time, okay? What does this represent? This is the forcing function. This is what's making everything move. What other torques are applied to the shaft or exist on this shaft?
Is the bearing mounted, or is it like, is there a normal force being created by the bearing?
It's mounted, and the bearing likely is also creating a normal force on this shaft, probably supporting it.
Like exercises in circular.
A normal force does not create a torque. So it wouldn't show up in this equation, it would show up in the linear translation one. Which, yes, multiple systems of equations multiple things going on at the same time. What other torques do we have?
It's the torque of K times.
We're going to have some amount of torque, some amount of energy that's consumed by the rotation of this shaft. Okay? And that is mounted directly to here, so we do have, let's see, we do have a minus K times theta, where here theta is represented by the rotation of the end of the wheel. What other torques do we have on this? I'm going to write this though as T spring, and that's going to represent the spring compression of shaft. Some people will actually model this as actually being a spring itself. Sweet. What other torques do we have acting on this shaft?
Torque from the bearing.
We do have a torque from the bearing. What's causing the torque?
Forcing function.
Well, the forcing function is causing the torque over here. But what is creating the torque in the bearing? Anybody know? It's not the normal force. You brought up the normal force? That one is not creating a torque because it acts perpendicular to the shaft. There's no torque associated with that. Cross product between the distance from that force and the force itself becomes zero. Is there another force present in that bearing? There's a friction force. So there is a friction force inside of this bearing where the friction resistance of rotation is, well, it's going to heat up the bearing, but it's going to consume some small amount of energy. So we'll say TB, and that stands for bearing friction. That's another torque. Do we have any other torques in the system? One caused by the moment of inertia, or the inertial torque. Okay, this is the equivalent to D'Alembert's force. And here I'm going to put this as a plus because I have reasons. It exists opposite of those for now. No, I'm just going to leave it at a minus. Never mind. Ignore me. I wrote it as a minus. It's whatever. Eee! There's a zero. We haven't talked about modeling yet. We'll get to modeling. And then hopefully this starts making sense. Now what I'm going to do is I'm going to take this equation, which is our system equation, and I'm going to plug in component equations into it. Okay? So what we have is sum of the torques is equal to, oh, nope, I'm going to erase that one. We're just going to go ahead and say the torque is a function of time, we're taking our forcing function out, is equal to Ts plus Tb plus Ti. Spring torque, bearing torque, inertial torque. Now what I can do with this is I can go over to our component equations and say this is the torque created by a spring. This is the torque created by a bearing. This is the torque created by an inertial component. So I just plug those in. Tt is equal to k theta plus b theta dot plus I theta dot dot. Well, that looks like a second order system equation. Now, what is the last step that I can do in order to turn this into a nice constitutive equation? Does anybody remember? Huh? We divide or multiply by something. Do you remember what?
Angular mass.
We divide by the angular mass. Why? Or the moment of inertia. You're going to be that guy. You need elbow patches now. Then people trust you. Why are we dividing by I?
So you can find theta double dot.
So we have theta double dot by itself.
Yeah.
Yeah. So here we're going to end up with your forcing function divided by I is equal to, and then I'm going to go ahead and rearrange this so that this one's first, this one's second, this one's third. This will be theta double dot plus b over I, theta dot plus k over I times theta. This is our constitutive equation. So I'm drawing a box around. Anybody remember this equation? This was on your homework assignment that was due. It's Sunday night. You had to use this extensively.
For zeta.
Yes, and guess what you're going to have to do next week?
I didn't think that.
Jeremy didn't need to.
I just plugged in the alpha and omega letters.
Shut up. Did you get them right?
No.
Nice. You do have to know what the alpha and omega are from here.
Yeah, but
It's an implied.
what alpha and omega are equal to.
Not always. Not always right. Whatever. Anyways. So here you get this equation, okay? And what we're doing is we're going to map this equation directly into this equation. So, in mapping that, what that means is, f of t is equal to your forcing function divided by your moment of inertia. That's your forcing function for the entire system. Okay? We know 2 alpha is equal to b over I, which means alpha is equal to b over 2I. Lastly, we know that omega naught squared is equal to k over I, or omega naught is equal to the square root of k over I. Okay? Now we can use the exact same solution method that we used for our electronic circuits. We're done. Do you calculate zeta? Zeta is equal to alpha over omega naught. This will tell you whether or not this is a critically damped, an overdamped, or an underdamped system. The same methodology that we used for critically damped, underdamped, overdamped systems, we have the same results here. Instead of current voltage, now it's torque and displacement. If I apply some sudden amount of torque, what you might get out of your displacement is you might get an angular speed that looks something like this, where your angular speed overshoots, undershoots, overshoots, undershoots, overshoots. What kind of system is this? Underdamped, critically damped, or overdamped?
Overdamped.
You just picked one of the three.
No.
Overdamped actually, it doesn't have the oscillation.
Critically damped don't run.
So it's critically damped.
Critically damped also doesn't have the oscillation. It is the underdamped. A critically damped system would look like this. Nope, my bad. Critically damped system would look like this. An overdamped system would look like this. Okay? So here, an overdamped system would take a lot longer to reach equilibrium, but it would not have the oscillation. An underdamped system is going to take a lot longer to reach equilibrium, but it's going to oscillate in the in-between. A critically damped system is going to reach equilibrium the fastest. I didn't talk about this last class, and I should have. Oh well. Dylan is watching the entire class. And I don't know why. Well, this is also true for linear translation systems. In a very simple model of a vehicle suspension, you have these three different types of suspension. Now this is, we're going to put this as displacement quickly. You have three different types of vehicle suspension. How many of you have ever ridden in an old truck? You hit a bump and you bounce for a bit? That's doing this. It's the oscillation. In that case, the suspension in that point is an underdamped system. Most cars aim for an overdamped system. Okay? When you hit a bump with an overdamped system, you go bang. Your vehicle suspension compresses and then releases. You go up a small amount, and then as you adjust going back down to earth, that's like two different systems. Okay? You have here hitting the bump and then leaving the bump. Instead of bounce, 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 and then coming down here and bouncing, bouncing, bouncing again. Which is an underdamped. A critically damped system would actually give you, it would give you a bigger jolt than an overdamped system. An overdamped system would feel more cushy. As you'll notice, you don't accelerate upwards as much. So here, if the bump is really small, you only reach here before you are already going back down. In a critically damped system, at that same point, for the same bump, you're already almost at equilibrium. So vehicle suspensions try to go with an overdamped system because you feel them less. It assumes that most of the interruptions you're going to see are going to be very small bumps. And as a result, it tries to filter them out. Okay? Now there is a problem when it comes to overdamped systems, and that is when you go to climb a hill, if you have too much of an overdamped system, here, it works really well when the bumps are small, but when the bumps are hill-sized, like you're still here, and then the bottom of your car starts scraping on the ground. Yep, that happens. Suspension is a fun business. But these type of systems all experience the same exact solution method that we saw for electronic systems. You come up with your zeta, you solve them, you're done. Now, zeta doesn't have as much meaning when it comes to systems of equations. That's going to be something that we talk about a little bit more. But this is going to conclude our review of dynamics and electronics. Okay? What I would do is I would encourage you, be very comfortable with this material. Review your notes. You're going to be solving these problems in the same ways for all 3 of your quizzes that are going to be going over this. Okay? So you're going to get a lot of experience with it. If you have any questions, come see me sooner than later, because we're going to be building off of this knowledge for this class. All right, I will see you on Thursday.